Right. So I think we should just change the goal slightly. And what we will do is we will do two things here. We will state and prove the Nakayama lemma, and then we will also prove the Kelly-Hamilton theorem, because they have a common principle and it's very important. So let's first get the Nakayama lemma and prove it. Okay. And we'll see what the principle is. Right. So there are two concepts here. One is the concept of a commutative ring. R is a commutative ring. Okay. And M is a module. Okay. So module I've defined earlier and you have read it maybe, but module is just a vector space, but the underlying thing is not a field but a ring. So M is such that M plus is an abelian group. You know this. And this dot is a map. It's okay to write that way also, but which is just to say that it's a scalar multiplication. Just a fancy way of saying scalar multiplication. This goes to something. And that's something we write at R dot M, scalar multiplication. Now we are in a position to give an example. Okay. This will be necessary. Knowing a module is necessary even to understand vector spaces in a nice language. Otherwise, we'll be stuck multiplying matrices to check everything, and everything would seem unnecessarily difficult. So, what is an example? Anyone? Example of module over a ring? Read about it quickly. Inform anywhere, but obviously Artin has this. But yeah, I'll just give an example. I've given earlier, but an example which is relevant in this.
So matrices and real numbers only.
Certainly, but that is just a vector space. So you're just saying vector space is a module, and where the ring is a field. This is a correct example. Yeah, I mean, that's the whole point. That's what we are generalizing. Yeah.
Sure, or we can do functions also, like like if you have a set of all functions over R,
right,
and then like if you take M, then we have this F plus G is G plus F, so it's abelian.
Correct.
Commutative.
But that is just a vector space again.
Yes,
So,
again, yes.
Right, that's a vector space. So we want some examples which are those are obviously important examples, very, very important examples. All functions are very important examples. But obviously we want to look at examples which are not vector space. Right? So what is that? So you take a vector space, okay? Take a vector space B, and you take your ring to be the polynomial ring. Okay? Fix a transformation T or fix a matrix, or maybe just take Rn as your vector space. Fix a matrix A, and then I will tell you how to define this. So, I mean, the obvious thing: x dot v. V is coming from Rn, and x is coming from this thing. I have to just define this, because addition is as it is, right? So this is as it is. Abelian group structure is as it is. Okay. But this is I have to define. So how should I define given this matrix? Remember, I have to return again a thing in Rn. I'm taking a thing from Rn, taking the variable x, and this I have to again return something in Rn. So by all means, this is the only choice, natural choice. Right? D is in Rn and A is a matrix, so this is again in Rn. Right? So I've told you how to define this multiplication, and now without much effort, you can just say that this is again just P of A at V. P of A is again a matrix, right? It's a huge polynomial, blah blah blah, but eventually it's a matrix after you're done everything. then this is also in R. So I've described how to define R, this R dot anything from this Rn. So this becomes a module. And this is the this is the module we will make for further study of linear algebra. Okay. If there are any doubts, please stop me and ask. But read up.
Sir,
Yeah.
sir, how did P of X dot V go to P of A dot V? Shouldn't it go to A dot V
So
again?
there is definition.
Okay.
Okay, this is no longer a day. This is sort of necessitated, right? So if x dot v is av, then what should x square dot v be? X square dot v will be something like this, right? Because all these rules should be followed, right? Associativity, someone to call it, right? Then this is av times x dot av. This is again a v, but then this is a square.
Yes.
So
Yes,
x
sir,
square,
yes, I got it.
and then you understand. So it sort of
Yes.
naturally follows, but I've defined it like that. And now you should check the axioms of the model. Please do that. You should check the axiom checking. Is maybe you cannot do it all the day, but at some point of the day you have to muster up the willpower and do it. Okay, and hopefully you'll start liking to do it, but you should do it anyway. So this is the thing. All right. So this is just an example. But now you want to state the Nakayama lemma, and you will see it Cayley Hamilton, so it's a good thing. State it. And erase everything. Proof is very quick. I am so phi. So phi will be a map. So obviously M and R is module and ring. Okay. Phi is a map from M to N, okay, which is just a module homomorphism. So you know vector space homomorphism, right? Any some phi vector space homomorphism. These are some basic rules. This linear. You obviously know this. Multiplication by matrix is like this, right? If you think of phi as a matrix, and then if you have a scalar, then it comes out. Right? Here also the same thing. Scalar R. So this is a module morphism. Module morphism. Okay. Then we want to say that right. That's quite important. Yeah. So there exists a monic polynomial. Okay. A monic polynomial in this. So now this is not a field anymore. It's coming from a ring. Coming from a ring. And yeah. Ring. Okay, right. It's coming from a ring. Okay. There is a monic polynomial. So in particular, it's not a zero polynomial. Monic polynomial is not zero. Right? Monic polynomial Px. So like polynomials with integer coefficients, right? They are examples which you have looked at. You have looked at polynomials with integer coefficients, right? This basic thing in high school also. You do Olympiads, you do high school polynomial thing, but with integer coefficients, number theory problem. This is just call it Px. Okay. Such that P phi is 0. And P phi you understand. P phi is 0. This is means 0 function. So you see phi is a function from M to M. Obviously phi square is also a function. Phi square here means phi composed phi. That's the thing, right? And phi 1 plus phi 2 is also a function from M to M. Right? Or basic. And so you can define P phi is also a function as a zero function. There, Kelly Hamilton was a zero matrix. Same thing. That matrix was a function. It's a function from R into R. And this is what we want. There is a monic polynomial which does this. Kelly Hamilton theorem is when you replace this by V so that you can see that it's not some, and phi becomes this matrix. That's the function. And then they have already seen this. Then we have seen a multivariable case of that. So this is an analogous to that. It's generalization. But how do you prove it? Obviously, M here is finitely generated. M is finitely generated. Otherwise, obviously, you cannot do anything. It's not finitely generated. So what do I mean by finitely generated? So I just mean that there are some, so just like vector space is finite dimensional, this is the analogous, but much more subtle or nuanced, but analogous. But we won't need the subtlety here. We just need that there are some things in the abelian group or in the vector space such that these can be generated over R. They will give you a right. Which what does it mean? It means that given, and this we will need. So this means these are generators. Basically, nothing else. Given any M, you can generate them by linear combination. Same thing, there's no difference. Module theory is not something advanced, not something. Not saying anything about uniqueness, not saying it's a basis, just that we're generating. Because basis may not exist. There's some strange object. But we don't need all that strangeness. That's the point of this lemma. Okay? We just need the formal, the easy part. That's what this is. So M is like that. And now we just use it. So I'll just hook up this polynomial for you. Okay? And this is where all your eliminations and determinants, adjoints, everything will come in. Okay. So we have to keep that. So you see phi of M1, I will write. This will also give a proof of Kelly Hamilton. So it's important. So this will be P11 M1. I was writing facts, very, very simple facts. Phi M1 is in M, right? A of V is a basis vector, again in M. Again, it's a linear combination. Pi's are obviously in R. R is a commutative. In fact, Hamilton first proved it, I think, for non-commutative. Some non-commutative ring, some quaternion ring. And I have not read that in some old paper. It will be easy to read now at this point. More than a century. And I'm just, why I'm writing it like this. I want to make a matrix out of it. If we get stuck, we will look at the book, but let's try to do ourselves. Please think of this if you're confused, if you are getting a little bit confused also, or anyways, think of it as just phi as a matrix, M1, M2 are basis vectors, these are again in the vector space, phi of Mi is again in vector space, I'm just writing a linear function. Nothing else. That's okay. Right. Now we want to make a matrix out of this. Yeah, I have to close the window. It's raining heavily. right? Yeah. Now we want to move forward. Now we will just write this as a matrix. Okay? One thing I will do, which will not destroy commutativity, I will start to write phi of, these are all just symbolic symbol gain. I will start to write it like this. Okay, right? I'll start to write like this. And you see, now you start to write like this. Then phi of anything in the ring is equal to this, right? Because it's true for every m that this is true. That is the definition, right? Because for every m, you know that this. The point is that it's, think of it like this. You have R, which is a commutative situation. You throw in phi and all its powers and additions and mix it with R. It's still a commutative situation. Right? Everything is still commutative. Okay, that's all I want. So with that understanding, we write like all right. With that understanding, we write like this. C12 dot 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 C1m. This is becoming a matrix. C21. And this is phi minus C22. Okay? And this is C21. And again, in the third row, you will see that there will be, just writing the third row also, C32. And here it will be phi minus C33 and C3n. And it goes on and on and on. And final row may will be phi minus Cn. Okay. So, I mean,
I'm not getting the next the previous three lines again. That Rn.
Rn. This one
Phi
here.
of
No, you said, oh, you mean this one. Phi of R is R of phi?
yes.
Right. So actually, my explanation here is slightly wrong as well. That is, I think, the reason. So the problem with my explanation is that this doesn't make sense because R is in a ring R and phi is not in that ring. So what do you mean by this symbol at all? Okay. So that is the problem, right? Yeah. So this is the problem. So, but you will agree with this is the definition. For what I need, I will not need that. But you will agree with this. This is the definition, right?
Yes.
This is the definition. Yeah. So let's just stick with this and move forward. If you look at this expression, there is again the same kind of problem, right? That this phi is coming out of nowhere. Okay. So then, how should I explain? Then I have to say that you take R and take the polynomial ring and put x in that. Should I do that? Let me think. Okay, then we will do that. Otherwise, it's not rigorous. Not rigorous. So you look at this. So first of all, you look at this matrix. Then I will say it properly. Yeah. I mean, I was just saying that if you agree to understand this as sort of another function from m to m, right? Which what does it do? It takes M and it sends it to Rm, and then it applies phi on it. Right. This is again a function. Phi dot R is again a function. If you understand it like this, then you will understand that these two things are, and this also as a function, right? Then these two functions are same. And this function would be first it multiplies by M, first it applies phi, and then it multiplies by M. Right? Then these two functions are same. Is that okay? Am I making any sense? So I'm saying that if you have a vector space B to B, okay, let me.
We can be clear that two functions are commutative.
Yes, that is coming from the definition. So let me say it in the language of vector space first. So you see, in vector space, if you say that because matrices commute with scalar matrices, you know that every matrix commutes with scalar matrix. That is what I'm trying to say. But when you take a vector space and you take this function which takes a vector and multiplies it by 2, so your field will have 2, right? So multiplies it by 2. This is a function, right? And then you take some complicated function which applies this, right? And then you can compose these two functions, right? So you have the function which is just matrix multiplication, and you have another function which is multiplication by scalar 2, just scalar multi, and you compose this. Okay, then you know what function you will get. It will just send it to AB, right? But then if you do it the other way, obviously you will get the same thing, right? And why? Because because scalars are going to commute with the matrix, correct? And in the case of ring also, the same thing happens. But if you take M to M and you take M and multiply it with R, you get Rm. This is also a module homomorphism, right? This is also homomorphism or linear map, whatever your language is. It's also a linear map, right? That's just coming from the distributivity law and so on, which is the definition of module. Okay, it's also a linear map. Okay, and this linear map commutes with every other map, right? Why? So let me say it on a new page. Okay. So we have two maps. One map is from M to M, and there are two maps from M to M. One is phi. Okay. Both are module homomorphisms because let's just check for this. Phi is by definition, and this is why, because you take M and you send it to R dot M. And now we need to check that it's linear. So this is the, remember, this is a function. Okay. And this is obviously this by definition. By definition, this function takes M1 plus M, and takes anything, multiplies it with R. Okay, but obviously this is this. Why is it? Because that's the definition from distributivity in the definition of module. So it is a linear map. Just clarified that it's a linear map, just like in vector spaces. Now, this map, let's just call it like this, so that you know, it's a function. Now you check on your own that this is also a function from M to M. That I'm not asking to check. That's true because composition of functions are functions, the composition of linear functions are linear functions. But you should just check that these two functions are same. And it's just easy. That these two functions are same because both will just send M to R times phi M or whatever. Yeah. That's all I'm saying. So in that sense, they are commutative. So they are commutative in the sense that I am viewing the elements of the ring also as functions. So that's what you have to do. These CIs are also functions, and phi is also a function. So everything is sitting inside the space of functions from M to M. Okay, and with that understanding, we are saying, but you don't have to see all that way, keep all that right in front. We just have to, when we need it, we will say. Is that helpful? Is that useful?
Yeah, the both functions are commutative. Okay, then why we are just subtracting the phi minus 1? That
Why?
too.
Yeah. So first of all, we can subtract, right? Because we are viewing C11 also as a function from M to M, and this is also a function from M to M. So we can subtract two functions, right? Linear functions. Now, why we are subtracting? What's the intention? That is a question which will be answered. Okay? Because it's going to answer the question. It's going to prove. Yeah. So they're looking at this matrix. Okay. And then we are writing all these things like this. So I have avoided that thing by telling you that this R sits inside this endomorphism thing, this set of functions. This is, so we are writing all this information in this matrix form. Okay. And here everything commutes. Phi commutes with everything. That's what we just said. So now you do your high school thing. Given a matrix A, okay, what is A times aggregate of A? Yeah, you know that it is everybody knows this. I times determinant. Hello? Is this fact about, is this fact okay?
Yes, sir. Yes.
Yeah. Yeah. Not
Yes, sir.
yeah, not asking for the proof, but you should know it as a fact. It's not difficult to prove. It's mostly just a matter of elimination. Yes.
Yes, sir. This was like this
Yeah.
was it's standard like
It's a,
12th
yeah.
grade. It's
Exactly. It's
CBSE.
standard. Yeah. It's a standard thing. And note here, you never need any division to prove. You never need to invert anything, right? You never need 1 by 2 or 1 by 3. It is a fact which is purely about commutative rings. It's true for commutative rings because that's all you need. In fact, it's easier to prove it for commutative rings because you don't need to assume it. Okay. So this fact is just, you will assume it here also. Okay. All right. Yeah. Yeah. So apply it for this matrix where the coefficients are coming from a commutative ring, right? This the ring that is generated by the CIs and phi is sitting inside the collection of functions. And I can write all that, but that ring is commutative because phi commutes with CI, and so you can apply it there. Okay? So with that in mind, you multiply by the adjoint matrix, and when you do that, then we are right in the same page. You will get something like this. You will get determinant of A, determinant of A is 0, M1 up to Mn. This is equal to 0, right? And what does this mean? Again, we have made an understanding, right? And with respect to that understanding, it means that determinant of A times M1 is 0. What does it mean? Well, it's fine. Determinant of A is also a function from M to M. Correct? Because these are all functions from M to M. And so you multiply them, it means you're composing them. Adding them means you're adding the function. So this function from M to M kills M1 and it kills everything. It kills all the generators. So it kills the entire module. It's a zero function. It kills everything. That is by our understanding. Right? Okay. So it means that the determinant of A, which we have just done, that from M to M is actually the zero function. Right? And it's obviously a polynomial in phi. Right? So this polynomial in phi is what? If some function kills the generators, then it kills everything that we understand for this linear. Okay. That is a Nakayama. The proof was so easy. So why was the proof so easy of a fact like this? First of all, is this proof clear? Like you have not done anything, it's written thing. That's all. So you see the proof.
Yes.
right?
Yes,
Yeah.
it's
So
clear.
the proof is easy because if you now look at Kelly Hamilton, then you have this A, replace everything by A. And the point is that you won't want to do this in maybe your BSc first year. You may have not considered a matrix whose coefficients are matrices. You would not be happy. But somehow you are convinced that you can do it. And that is what making the proof easy. Sorry, I mean, probably I'm messing up with the same A again 2 times. I'll call this B. Or yeah, I don't know. Maybe this A should change. Better to change this. But that's a different. So through this language of ring theory, we have convinced you that you can consider matrices whose elements are matrices. Because pi is actually a matrix. In case of vector space, it's definitely a matrix. I mean, it can be represented by a matrix, right? Up to all sorts of isomorphisms, whatever. It's completely like a matrix. And we have put it in a matrix. Okay? But the thing is that this matrix commutes with everything that is there in the matrix. So it's again a commutative situation. And that is all you need for all your determinant identities to be true, wherever inversion is not involved. And so we have proved your Kelly Hamilton like nothing. I mean, this is the Kelly Hamilton, right? This thing is your matrix A minus identity. You have to think. Or no, something is wrong. Let's see. Have we proved? Okay. Yeah, Arnav, you have a question?
Yes, how we get that determinant of A dot 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 A into M1 M is equal to 0 under this line.
Right. So why is that happening? Because yeah, how did A come? What is A? Sorry. This is X, right? Yeah, this is X. So I should say determinant of X.
Oh, but how it's giving us 0? Multiplying determinant and the M1 giving us 0. Why?
Okay, because you have taken this X, right? So you have X times this thing is equal to 0. So I've just multiplied on the left by adjugate of X, right? And this side also I've done that, but you know that. Yeah. And this thing,
X times M1 M2 is equal to 0. Where we are getting that?
okay, that is this thing, right? And that we are getting from this thing.
X.
Yeah, that we are getting. So basically, this thing, you bring everything to one side, and then you're writing it in the form of a matrix. That is an understanding we are making, that we will represent that by a matrix. Okay, because that makes things more convenient. Okay, and all the rules of matrices apply, like associativity and so on, are still true. This is the thing about matrices. Otherwise, without matrices, how will you talk about it? Give you a uniform language to talk about it. That you bring everything to one side and then you have a system of equations which is equal to 0. But when you write it as a matrix, then things become, then you can do something with the matrix. Okay. So remember, even while proving the linear independence and so on basis, we did similar thing. We had a matrix which has vectors, which entries were also vectors or something, right? And we did similar. And the thing is one of the key, because we get to use all the associativity, and now we are using determinant of matrix. Okay. And yeah, that does the job. So I mean, I'll stop here. So this is the Nakayama lemma, and we'll stop here. Maybe we can meet after 5 minutes and prove the multivariable Kelly Hamilton. Yeah.
Yes, sir.
Okay. So yeah, and how this implies Kelly Hamilton? Just try to figure out. I can say, but maybe I'll see.
Can you just show the next page for us?
Yes. Yeah. Have a look, and when the meeting ends, and just join after 5 minutes.
Aryan? Aryan, are you there?
Hello. Yeah. Yes. Yes, Anup.
So how sir conclude the last thing?